Okay. Well, welcome everybody. Thank you for being here. This is our talk on high-performance graphics and text rendering on the GPU. I'm Barbara Geller, and this is Ansel Sermersheim, and we are going to be your presenters for this talk. Oh, look at this. Okay. So we're going to talk about graphics, and it is a wide subject. And one of the things we want to make sure we do is define what graphics are, because it doesn't have just one definition. It's also really important to know that if you are somebody that is developing software, and if you have anything on the screen or do anything that does a computation, you need graphics. I think that pretty much covers everybody. So if you don't calculate anything and you don't display anything, graphics aren't that important. So I think we've only lost 2 people at that point. We also have a demo we're going to show you. So that should be pretty exciting. We're going to take a risk on that. And we're going to talk a lot about the graphics terminology, which can get really complicated really fast. And we're going to try to break it down in a way that makes sense. And let's just get started. We want to start with who we are. We are the co-founders and the maintainers of the CppCon project. Is everybody heard of CppCon? Oh, cool. We've got some of our team members, so a few people don't. Cool. Yay, team members. CppCon is a set of cross-platform GUI libraries. Now, it is more than just a set of GUI libraries. There are other things you want to do, but basically, if you think about it as a set of GUI libraries, and again, all different platforms. We've also developed a string library, which we introduced a couple years ago here. CS string is a drop-in replacement for STD string, and it will give you Unicode aware. So you don't actually have to wait for STD text. You can use it right now. We have a couple other libraries. We've also developed DoxyPress. DoxyPress is an application which will help you generate documentation, which is going to get very interesting in C++20 as we start getting into modules and other things that are going to become harder to generate the output of documentation. And we will be maintaining DoxyPress that will work with C++20.
Everything we do is open source. And to the extent possible, we make sure to use absolutely modern, cutting-edge C++ techniques in everything we do. It's all on GitHub, and you can get pre-built binaries for almost everything on our download site.
So earlier this year, we released 3 videos, and they were 3 videos on graphics. We suggest you take a look at those at a later time, because they're really quite interesting, talking about the evolution and the timeline of graphics. And that actually does play into how graphics evolved and what really drove the graphics industry. Now, we're going to touch on that a little bit in our talk, but these videos do a really nice job of also explaining what changed in the hardware, and that does influence graphics. So what are graphics?
Well, broadly, you can divide them into 2 different categories. And it's a very sharp distinction. There's raster graphics, which are a bitmap image that consists of a whole bunch of pixels, individually addressable, and you manipulate these bitmaps usually on the CPU. That's traditionally been what happens. There's also vector graphics, where instead of a set of pixels, you have coordinates that form a shape, a polygon, a triangle, or whatever. And the drawing commands are actually based on the mathematical equations that define that shape. And this really should be processed on the GPU. If you're doing vector graphics, that's what it's good at. Because on the GPU, the vector representation will be transformed into a rasterized representation and sent to the monitor for display. But you want that rasterization to happen as late as possible. You'll see why. The really fundamentally awesome property of vector graphics is that when you scale them or transform them, the image quality isn't compromised because you're just adjusting the coordinates. Now, 15 or 20 years ago, the monitor you would find on everybody's desk who had a good monitor was VGA resolution, 640 by 480, 300,000 pixels. And it seemed really good at the time. Now, most people have a monitor somewhere between 1080p or full HD or whatever you want to call it and 4K. It'll be somewhere in that range. Now that's talking about 2 to 8 million pixels. So that means if you have an application full screen and you change something and the whole screen needs to get updated, that's potentially 8 million pixels that need to change before the screen reflects that change. And you really want that to happen 60 times a second, ideally, for smooth animations. 8K monitors are coming. You can buy them now. They're about $4,000 a piece. They're not a commodity item yet, but we all know how hardware prices work. They'll be commonplace soon. That's 33 million pixels you have to render 60 times a second to have a smooth application experience. That's a lot. So why does this matter?
Well, it matters because most of us are doing all this work on the CPU. And a CPU has 4 to 8 cores for an average CPU. And yes, if you have a high-end CPU, you are looking at something about 10 to 20, and if you really have a lot of money, maybe 32 cores. Which means typically, on a CPU, you're running 1 to 2 threads.
Per core.
Per core. Now, how many people were aware that an average GPU has over 1,000 cores? Some people were aware of this. This computer right here is a 2-year-old gaming laptop, and it has 3,000 cores.
Moreover, these GPUs are hyper-threaded to hide memory latency. So to keep this GPU busy, you need 50 or 60 threads running per core, which means you need an API that allows you to start 100,000 threads to render an image before you can actually keep this GPU busy.
So the idea is we should be moving more of our work from the CPU to the GPU. And that's what we're introducing, and that's what we're going to be talking about how to do. Go for it.
So up until now, the gaming industry has really been what drives changes in graphics. The consumers of high-end graphics cards tend to be high-end gamers. And over time, changes in the GPU hardware has meant that the way we work with the hardware has to change. And games have kept up with this, but the general computing environment has not. And that's important because graphics are more than just explosions, robots, and lightsabers. Everything you see on your screen is graphics.
Yes, everything.
Is that important to a user of a desktop program? Well, if they want to actually see something on their monitor, of course.
And the gaming industry really pushed the developers of the drivers and of the graphics APIs. And we owe a lot to the gaming industry. Unfortunately, they really pushed things, which means more things in new graphics APIs have to be done by us. And this gives you great flexibility, but it means more work if you want graphics in your applications.
But as a GUI developer, doing graphics on the GPU gives us a lot of nice properties. We get high DPI support for free, which is really important and becoming more so as monitors get bigger. You get a responsive user interface because the GPU is designed to deal with large amounts of data like this. Smooth scrolling of text is really important. You get all these nice properties when you decide to render your application on the GPU.
So we would like to show you a demo. We're going to take a risk and stop the slides and bring up a demo that we wrote using C++17, because that's where we should start. And it is using CMake as its build system. It also uses SDL2 library. And that's used for the window management and for the keystrokes. If you're familiar with GLUT or glue or however you pronounce GLFW, you could use that. We just chose SDL2. So insert demo. Here's our demo. There's a pot, and there's a table, and there's a salt and pepper shaker, and there's a chalkboard with text. And each of these are individual items. The text is not an image. This is text that is being rendered on the GPU. The pot is a 3D image, so let's take a look at it. This was actually rendered, it is actually being rendered here the actual drawing and the creating was done in Blender. And Blender is a 3D modeling program. But the only reason why we used Blender was to create the mesh. And once we created the mesh in Blender, then we took that as an output and we have brought it in. So all the rendering is here. Yes, we have a question.
You said it was a 3D image. You do mean that is a triangular mesh and not a signed distance field, right?
That is using triangles.
Okay, yeah.
How many triangles? About 10,000? Oh, I'm sorry. The question was how many triangles are in the mesh for the pot? And I believe it's about 10,000. We can actually look that up and check it, and we can show you the output. Actually, we're going to provide the demo for you, so you can actually play with it. What's interesting is the salt and pepper shaker are each individual meshes. The tabletop is a mesh, and the table is a mesh. So those are individual items. The fact that they're sitting on top of each other is strictly because that's where we put them. May I have my tea, please? Now, what's very interesting is let's play with the pot a little more.
Now, this is nothing that you couldn't do with a 3D graphics engine that many games use. However, something that they don't manage as well is text, which is obviously very important if you're going to develop a GUI application and render it on the GPU.
So what we want to do is, if you can imagine the camera, which is really there, it is in front of the screen. So now what we're going to do is we're going to put the camera on a track, and we're going to pull the camera in. And here we are looking at the word demo. So what you are seeing is the event system in our demo program is responding to just keystrokes, just left and right arrows. We have now zoomed in on the word demo, and there's no artifacts. And that's how you want to do high DPI. Question is, how are we doing it?
And if you zoom in even a little bit further to a point where it doesn't even fit on the screen, you can see the edges of the text are still sharp, it's still readable, there's no blurriness. This is what you ought to have when you render text at any scale in your application.
So again, this is not a PNG. This is not just, we're not just faking the word demo. This is a quoted string in our demo program, and it is being rendered in the program that we wrote. And the high DPI that's happening is simply because we're adjusting the scaling. Let's go back to the slides. It worked. Cool. I'm impressed. We've never done a demo in a talk before. So what does the demo consist of? Well, the demo has a CPP file, about 60 lines. We're going to show some of that code. There's an include file, about 60 lines. And there is a data file, which is where some of the calculations are happening. One of the other things that we have is there is a prototype file. So when we release the code and we show you the demo, there's a prototype file. Everything in the prototype is being moved over to where? To our library. This is running with a library that we have created. And again, we did mention that it links with SDL, but what we're really showing is this demo is being driven by CS Paint, which is an API and a library that is sitting on top of Vulkan.
And what we've done is we're releasing an open source BSD licensed library to encapsulate the Vulkan API and provide a higher level API that still reflects what you need in order to generate high performance applications with modern GPUs. It uses Vulkan HPP, which is really nice. It's the C++ interface that ships with Vulkan, which very few people know about. And most tutorials you'll find use the old C interface. I had gotten part way into designing a few things and just banging my head against the extremely awkward C interface. And Barbara said, there's a C++ interface, you know. I said,
Why aren't we using that? Yes.
And I went and threw out all the code and started from scratch again because it was so much superior to the C interface.
The other thing that CS Paint does is it does link with a library called GLM, and GLM is for the linear algebra. Now we do bundle that with CS Paint. So again, this is a new open source library we're releasing that will sit on top of Vulkan. So you don't have to do all the low-level setup that it requires to use Vulkan, which is quite tedious and a lot of work. CS Paint is platform independent. There are drivers that work with Windows and Linux. If you're using Mac, we're going to make CS Paint work with Molten VK, which is a wrapper into Metal. It's a translation unit. So again, everything is going to be using Vulkan at the lowest level.
So instead of doing all the tedious and repetitive and often repetitive and very tedious parts of Vulkan,
are they repetitive?
yes,
Yeah.
and quite tedious, and there's a lot of boilerplate. You'll be able to do a few straightforward API calls into a modern C++ library and put something on the screen.
Which means you get to concentrate on writing your shaders or doing your modeling or your business logic. What we're doing is abstracting away the tedious parts. Yeah.
And the repetitive
and
parts.
the repetitive parts. Yep, that's what I thought. Why Vulkan? Why not?
Vulkan is the right choice for the future because OpenGL, which Vulkan is sort of related to and loosely based on, was a graphics API that was developed decades ago, and it was very cutting edge for its time. Unfortunately, GPUs have gotten faster to the point where OpenGL is unable to keep them busy. Because OpenGL is too synchronous. You have the CPU spending a lot of time waiting for the GPU to finish its work. And then the GPU is just sitting there idle, waiting for more work to do. So we need an API that actually exposes the parallelism in this system and lets you run things on the GPU and the CPU simultaneously. Unfortunately, that means it's much more complicated. This places a lot more burden on the developer. For example, there's no built-in memory management. You have to decide how to allocate memory on the GPU. There's no fixed function pipeline. So even when you're first prototyping something at the very beginning, just to see a triangle, you have to implement all these various parts to get anything on the screen.
It's about 700 lines of code just to get a triangle, just to get everything in Vulkan to set up everything you need. It's about 700 lines of code, and it's tedious. Yes.
Yes, it is.
Yeah.
And there are almost no defaults in the API, so you have to make so many choices as you start working with Vulkan, many of which you may not even understand the terminology that's being used when you make these choices. The nice thing is, it's an absolutely identical API for Windows, Linux, and Android. And as mentioned, there's a translation layer that allows it to run seamlessly on OS X. And it will take advantage of the power of the native GPU on each of those platforms. So we get a lot, but we have to put a lot into Vulkan in order to get this.
We should have a library.
We should.
It's a good idea. So here's the setup for the demo. We're going to show just some of the basic code, but that's the entire setup in our demo. So this is all you would need. Now, this is the equivalent of the 700 lines of code. And it's just abstracted away in CS Paint.
So
The first two lines of code are initialization. This kind of looks like C++ because we wrote it that way, and because it's accessing a C++ interface into Vulkan.
So we have a nice, clean, value semantic interface into the complexity of the native API.
This is the event loop. Now, we didn't put everything in here, but as he was rotating the pot, he was just using left arrows and right arrows and spinning it. So that middle section of processing the keys. But this is just a standard event loop. We are using SDL to get the keystrokes. The only thing we wanted to draw your attention to is the draw frame, which we're going to talk about what exactly the draw frame does. But that's the thing you would need to write, is the draw frame, because that's all the commands. Okay. If you've never written a fragment shader, this is what one looks like. And it's not a lot of code, but it's not written in C or C++. This is written in a slightly different language with a slightly different output. But we're supplying it in the demo, and it's actually not that complicated to read. But the shaders are one of the things you would need to write, and they're what control whether it's the lighting or the coloring or how something is done. This is the exact fragment shader we used for the table and the pot. It is not the fragment shader for the text.
And we'll show you why later. But the point of this, even if you've never seen a shader before, is hopefully to come away with this presentation with the idea, it's not scary, it's not complicated, it's a slightly different language, but it's not a ton of code. So when you hear, oh, I've got to write a shader, well, it's quite straightforward in many cases.
So here's where it gets complicated. And this is the graphics terminology. And to really program in Vulkan, you would need to understand all of this. And not all of it is available in terms of looking it up on the internet. You can't just go and query all these different things because information is scattered all over the place. So what we've done is assembled a lot of this information in these slides. We're just going to run through these very briefly, but to expose you to the terminology that if you were using Vulkan, here's what you would need to understand.
So you can have sort of a high-level overview of how these different pieces fit together in order to render a scene.
What's really important is understanding what an instance is.
An instance is a very fundamental concept in Vulkan because it's actually your connection to the Vulkan API. Normally you only have one, and if you're familiar with OpenGL and you're going, well, where was the instance in OpenGL? It didn't exist. And this is one of the really useful things that was added in Vulkan, because everything you call in Vulkan relates to a particular instance that you've created. And so it gives you a container where everything is related to. Typically you only have one.
The reason why we wanted to bring up the term of surface is because this is the terminology that is used of where things are rendered on the screen, and it needs to be on a surface. You can't just take graphics and just put it on a random window. Vulkan output has to be on a surface.
And since the exact way to create a surface varies from platform to platform, this is actually handled in an extension. And this is an odd thing because it's an extension that's part of the standard. But it's still considered to be an extension because it behaves differently on different platforms. And abstracting away that difference is part of what we use SDL for.
We're just going to, again, briefly talk about some of these things. The memory heap is really important, though, because you have to control all the memory. You can't just write things to buffers and wherever you want.
So Vulkan actually differentiates between the concept of a buffer, which is a conceptual thing, and the memory that buffer actually lives in. They're two completely separate objects. So if you want to store some information, you have to create a buffer of the appropriate type. Then you have to allocate memory of the appropriate type, bind them together, and copy information into it. And this is useful because you might not have enough memory to store something, so you can have buffers that don't currently have any memory allocated to them, or you can move it from one place to another. All the memory that's visible to the GPU will be visible in a list of memory heaps that you can query Vulkan for. So you can find out about all the different areas that you can store things. And certain heaps have different properties, so you can only store certain types of buffers on them. And this is very complex to get right, and this is one of the things that our library manages for you.
So you don't have to actually control the memory heap. We've actually put that in the library. The library also contains information in terms of dealing with a vertex buffer and a uniform buffer. And the vertex buffer is where those meshes got loaded to. And the uniform buffer is actually used to actually reposition a mesh on the screen.
And I'll reiterate that second part because a vertex buffer, the name kind of implies what it's for. It's a buffer that contains information about each vertex in a particular shape. But the uniform buffer, it's kind of an odd name. It actually means this is a piece of data that applies uniformly to every part of this shape. So I want to uniformly move it from this point to this point, or scale it by a certain factor. That's the reason for the name, but it's kind of an odd name when you first see it.
So we were talking about a shader, and again, it is a specialized language. And in OpenGL, if you were programming shaders, you did use GLSL. And in Direct 3D, you were probably using HLSL. In Vulkan, you can use either one. We are actually using GLSL. And the bottom line is, there are various compilers you can use, and this actually comes with Vulkan. And the point is, it needs to compile to an output of a SPIR-V binary format, which is sort of just, that's the format, and you really don't need to know what that format is. But when you write it in this language, that's the output, because that's what Vulkan needs.
You can sort of think of SPIR-V as the object code for a shader, which is what you need to feed to Vulkan when you configure things. But what actually is a shader? Well, a shader is really just a callback. But it's a callback that runs on the GPU millions of times for each frame to render a certain part or certain aspect of the image.
And there's various kinds of shaders. And we're going to use, oh, there we go. So there's a vertex shader that's required, and there's a fragment shader. Those are on the top and the bottom. The two in the middle are optional. And there are times, and you would know when you need them, if you need to modify for tessellation or geometry. But the ones we want to focus on are the vertex and the fragment. And those are the ones that we used in our demo. And we're going to speed it up a lot. There's a pipeline. And the pipeline has a connotation of, well, I just put everything in the pipeline and it works. Sort of. But a pipeline is what you need to set up. And again, this is what we have abstracted in CS Paint. And there's a lot of information, as you can see, the shader handles, the descriptor sets. All of this information is configuration. And that's what's going to go in with these draw commands into this pipeline.
It's important to note that pipeline is a generic term that's used a lot in graphics. In Vulkan, a pipeline is a specific object that you create that contains a lot of information about how you want to render something. It's not just a generic term, we're putting it in the graphics pipeline. It's an actual thing. Well, what do you do with a command line and a bunch of drawing commands that you want to execute? Well, you have to put them in a command buffer. And a command buffer is a structure that you can put commands into and then send them to the GPU so they get executed. Now, the GPU is not synchronous with the CPU, and we don't want it to be, remember? So we need a way to explicitly express synchronization when we need it. And that comes from fences and semaphores. There are two types of barriers provided in Vulkan. So this gives you the ability to express dependencies. This has to complete before this, or I want to wait until this is done. But you have to explicitly state that if you want that property.
And again, the fences and the semaphores, they're all handled in CS Paint. So again, there are ways of overriding the ones we put in there. And that just depends on your application. But for the most part, you can use the ones that we set up. Then there's a frame buffer. And the frame buffer is where the output is going to be rendered to on the GPU. And that's the frame buffer is then what's going to get presented.
There's a big difference between Vulkan and previous graphics APIs. In Vulkan, there is no default frame buffer. It does not create one for you. It's optional, which means it's completely normal to have a Vulkan program that produces no graphical output at all. That's a supported use case. But in this talk, we do want to generate graphical output like you saw. So we have to set up a frame buffer in order to render, because the frame buffer is where the GPU puts its output when you're working with graphics.
There's also a depth buffer. And this is where we get the perspective. So when you saw the pot and we rotated it, you could see what was going on and see the inside. What was really complicated for us is when we first did the mesh for the pot, we only put one handle on it. So we could rotate it around, so we wanted to see the handle spinning around. And that didn't work. And in fact, every time we rendered it, it was different. Sometimes it was see-through, sometimes it was inside out, sometimes the handle was always in the back. It really didn't make a lot of sense. And we struggled quite a bit of what's wrong with the depth buffer. which by the way was very hard to search and type into a Google search of why is my depth buffer transparent inside out and the handle in the back. And this took about 5 days to figure out.
We had a lot of artifacts. We knew that.
Yes.
We knew the depth buffer wasn't working right. And Barbara finally found, she said, wait a minute. Did you know the z-axis is different in Vulkan from every other graphics API? I said, no.
My gosh.
Well, it turns out that in Vulkan, in every prior graphics API, the z-axis goes from 1 to -1. In Vulkan, it goes from 0 to -1 for some reasons having to do with floating point precision. It's actually a good decision, but it's different from every other graphics API.
So you changed it, and
So
it worked.
I fixed a couple of matrices, and I changed some of the math around.
And it still didn't work.
Ran it, and it made absolutely no difference.
No difference. So then I went
Okay,
back
let's
to
try again.
searching the internet again of why is my depth buffer still not working now that I have the z-axis correct? And I looked at him and I said, hey, what is your min and max value for your depth buffer?
Because you can clamp the z value to a minimum and maximum. And it turns out that the example that I had originally found of how to fill in that buffer was a two-dimensional example. And so I was clamping the z-axis to 0. Fixed
No
that,
depth.
and all of a sudden, all our artifacts went away.
went.
This is how frustrating it can be to work with a 3D API as low level as Vulkan, because there are so many things that have to be exactly right before you get rid of all your artifacts. And if you misconfigure the depth buffer, it is a mess.
It is a mess, yes. So there's a render pass. Not going to spend too much time on the render pass because I can see the clock is ticking. And the render pass does exist, but it's mostly for mobile. And if you're on mobile, it is one of the greatest things that was added to Vulkan. And it has to do with if you're doing tiles and if you're rendering on a tile base.
So this increases performance by many orders of magnitude for complex scenes on a mobile device.
Yes. There's also a swap chain. And this is another set of buffers for the GPU to render. If you're getting the idea, there's a lot of terminology, there's a lot of buffers, and it's quite exhausting to set up Vulkan.
And the swap chain is how you create frame buffers. Without a swap chain, you can't display anything.
Next. So there's queues now. And now we've got graphics queues and present queues and computation. Again, just a lot of things that you need. This is still part of those 700 lines of code. We don't have a triangle now. We're just talking about the queues.
What you need to know about queues is queues are the places where you put command buffers. It's a queue where you have access to the input, you can put commands in, and then they come out on the GPU and get executed. And there are different kinds of queues that are good at doing different kinds of operations. And it's very important to queue the appropriate command for the correct queue.
Synchronization. Remember I mentioned we were looking at the demo, there was a draw frame, and there was a call to draw frame in our demo. Draw frame is one of the things you would need to implement. And the draw frame, as you can see, is responsible for things like retrieving the frame buffer and building the command buffer. So that call, and we have that in our demo, and there's various ways. It's actually not that complicated to set up a draw frame, especially when we have examples of how to do it.
And it's responsible for doing all these things which create an image in a frame buffer, and then you have to get that image on the screen.
And we did talk about the fences and the semaphores a little bit. The key difference is a fence is a barrier between the CPU and the GPU. And you can query that, and you can change that, and you can do a lot with it. Semaphores are a barrier on the GPU that you can set up, but you can't really do anything with.
So if you want to synchronize the CPU with the GPU for whatever reason, you have to use a fence. If you want to synchronize two operations that are occurring on the GPU, but you don't care when it happens in your program, you just want to make sure they execute in the right order, you use a semaphore. It's cheaper, it's less expensive, it's faster because it's entirely contained on the GPU hardware.
There's also winding directions. We got this wrong too. The winding direction is which way am I drawing the triangles? And most people, and in OpenGL, the default was clockwise. So usually you do this clockwise. You have to set it in Vulkan. So if I'm drawing the front of the moon in triangles, and I'm doing it clockwise, then the back of the moon would be counterclockwise winding. And this has to do with back face and front face culling. Culling is the idea that if I'm showing the moon, I don't necessarily need to render the back side of the moon unless I need to see through. So if I don't need to see through the moon, let me turn on culling so the back side of the moon doesn't show. Well, if you get this one wrong, it messes up too. We had the winding set to clockwise. We had culling on, and we had nothing displayed. We had a triangle that was supposed to be there, and it would not render. Again, trying to search the internet, why doesn't my triangle show up? Was a bit exhausting. And then we found out why.
Literally, why?
Why? Why?
Because in Vulkan, the y-axis increases downwards. So we thought the triangles all had clockwise windings. They did if you had put them in an OpenGL program. But in Vulkan, it was upside down, therefore the vertices were coming out in a different order, and all the triangles were culled.
So the program was doing exactly what it was supposed to do, display nothing.
When backface culling works, it's great, because it throws out half your triangles before they're ever rasterized, which improves your performance by 50%.
Very briefly, these are 4 other things: push constant, scissors, extend, and viewports. Just more terminology, more things you need to set. We almost have a triangle on the screen at this point.
Getting close.
But let's talk about how it really works. Okay, here we go. Okay, so let me get this straight. I take the mesh, I generate the mesh in the model program, and then I take the mesh and I put it in the vertex buffer. Is that right?
Well, you have to allocate the buffer and allocate the memory and copy the buffer in there and bind them together.
Okay, other than that, I have a vertex buffer.
Okay.
Now I did a uniform buffer because it would be at 0, 0, and I want it to move over. So I do a uniform buffer that modifies the translation of everything. Is that right?
Sounds good.
Okay, good. So I leave that just sitting there. Okay, then I write my vertex shader. I don't want a fragment. Well, I do want a fragment shader, right?
Yep.
Okay, I want a fragment shader. I want a vertex shader. No geometry, no tessellation.
True. That's
Okay,
fine.
so I just write the shaders and leave them there.
Well, you've got to compile them.
Okay, I compile
and
them.
load them.
In my build file.
Yes.
Okay, and then I load them. I don't load them quite yet, but I need the descriptors. I need the face culling. Wait a minute, descriptors. I also need a descriptor layout, a descriptor set.
Yeah, we kind of glossed over that because you might not have the buffers ready when you want to set things up. So you have to have a descriptor that describes the buffer that will eventually be available when you go to render the pipeline.
Okay, so I have the descriptors, I have the face culling, and I also need the scissors, the extent, and the viewport, which we didn't even show, and the fragment shader, and the vertex shader, and I put those in a pipeline.
Yes.
Okay, good, so it's all in a pipeline. Then I take those draw commands from that draw thing that we showed earlier, right? So a draw command, but I need my fences and semaphores. Okay, so I got my fences, my semaphores, my draw commands. And then I put those in a command buffer, which is on the CPU. So I just copy that?
You call commands, it goes in the command buffer.
Okay, that's on the CPU. Then I have to put it on the GPU in a graphics queue, not a presentation queue, not a computation queue, which you did wrong the first time. Yeah, you did. It's a graphics queue. So you put it in the graphics queue. Now, can I have coffee?
No, you're not done.
I'm not done. Okay. When will it be in the frame buffer?
At some point,
When?
when the GPU's done.
Then I have to query the fence,
Yep.
not the semaphore.
Right. Because
Okay.
you need to know on the CPU when it's done rendering.
But did you set up the frame buffer when we started the initialization?
Yeah.
Okay, good. You set up the frame buffer. I'm glad. Now I can have a glass of wine.
Well, actually, yeah, you can. Make sure you don't come back from that glass of wine and change the vertex buffer or the uniform buffer before the GPU is done with them.
But I need to change the uniform buffer because you pressed an arrow key and you rotated the pot. So I need to interrupt the frame buffer and I can actually do the uniform buffer.
Well, so you have two choices. You can either wait, or you could make another uniform buffer and put that in the next frame, and then swap between them.
Do I have to do a new pipeline?
Probably not.
Okay.
Depends on what you want to change.
So if I'm going to change the uniform buffer, then I can, this is exhausting. Oh my God. Why don't we just write a library?
Sounds like a really good idea.
So the way that it actually works in our demo, okay, is we actually have one pipeline, one vertex buffer, two uniform buffers. And that when you press the arrow keys, everything changes. And we do have to wait. But what we're doing is we're actually setting up a frame buffer. And we're actually letting that sit there, and he's got another frame buffer, so that we can be generating the code for one frame buffer as the GPU is working, get the other one ready so we can present this one and present this one. If the program is sitting idle, we're still doing it back and forth. We're using 2 frame buffers, and that is dependent on your GPU. It might be advantage to use 3 frame buffers. But you need to be careful not to touch the uniform buffer, because although you've sent everything to the GPU, it's working and you can't disturb it. Sound good? Are you exhausted? Yeah, we actually did that. Okay. So what's really important to us is putting graphics back in GUIs. Because we've lost graphics because we're rendering too much on the CPU. And the question is, how did we do this? Because text is just graphics. And CS Paint can render text on the GPU. It's more efficient and it's cleaner edges. Here is a screenshot. This is off my Windows machine. It is a screenshot. This is using a 16-point monospace font, which I believe should be readable. And this is just a screenshot. We didn't alter it or anything. We just did a capture. Then what we decided to do was to blow it up. 1,400%. This is readable on a Windows application. But this is with no high DPI. This is with no adjustment. This is what that rendering actually looks like. So this is what you're getting. So if you're running an application, and it doesn't matter if it's Windows or Debian or any platform, if you're running without anything, any high DPI modifications, and everything is happening on the CPU, this is what you're getting.
Now, most people aren't running at 1,400% scaling. Most common scaling factors right now are 200, maybe 400. So it's not as obvious, but there's a lot of blurry text out there if you really look for it in various applications on high resolution displays. What happens when you do this on the GPU? Just scaling up that original font on the GPU.
Just as we zoomed the camera in on the word demo, this is that capture.
This is obviously better. Now I'd like to stress, this is actually scaling up a low resolution font for display on the GPU. The only difference is on the GPU we have so much computing power, we can apply more and smarter scaling algorithms to this font and give you a crisp, readable image.
Do we like one or two? I think this one looks a lot better. And it's easier because if you have an application that has 3 or 4 different fonts and you're going to try to figure out on the CPU how to do this, you're going to be spending all your CPU time trying to figure out high DPI, which is what we just went through in CppCon. In CppCon, we tried to modify this by using scaling factors. It works, but you have to scale everything. And it's not as crisp as this. So this is what we want to change, is we want all our text rendering to get off of the CPU and move on to the GPU.
Which means we only need one size for each font, instead of generating an image of the font at a whole bunch of different sizes, which is expensive in memory. It uses a lot of memory.
So what's interesting is how this works. And we had heard about one of the ways to do this with the distance field stuff. But it turns out there's an even better way to do it. And that's the multi-channel signed distance field algorithm, which is a lot newer.
So what we actually do is we generate a low resolution image of the font. And there was an older algorithm called signed distance fields, which just sort of generated a blurry image. And from that blurry image, in a fragment shader, you could decide whether you were inside or outside the particular letter that you were drawing. So we make a whole rectangle, or in our case, 2 triangles, doesn't really matter. And for each pixel, we need to decide, are we inside or outside the letter we're drawing?
Now it's important to know that when you mention the rectangle, we're drawing one rectangle per character. So for every character in a string, and when you look in the demo, it is just literally a string. And we take every character, we create this rectangle, and we're basically using the equivalent of that image as a texture. But it's not a normal texture in graphics like marble would be, or a wood grain that you would use to texture something. But we are using this generated sign, multi-channel color signed distance field algorithm. We are using that in combination with the texture of the fonts.
And the multi-channel part solves the problem that the original sign distance field rendering gave very rounded corners for all sharp corners. It would round off every corner. The multi-channel uses the red, green, and blue channels of the texture as separate distance fields to accurately reproduce sharp edges in the original font using very little information and a very low resolution copy of the font. And this is all in CS Paint, available for you to use.
Now, if we did generate one font, and that's part of CS Paint, the script to how to take just a regular font and turn it into the equivalent of this texture, that is included in our demo. So we do have the script. It's not that complicated, and the file is extremely small.
Are you creating that texture on the CPU?
No. The texture itself, are we creating the texture on the CPU?
Currently we are. The texture is actually generated, is pre-processed.
Pre-processed.
That is, we'll get to that.
Yeah. But the actual, when we're actually overlaying everything and we're putting the texture and doing the modeling, that is obviously on the GPU. Yes?
If the text is just black on white, then why does it matter if you use multiple channels?
Good question.
Good question.
If the text is just black on white, why does it matter if you use multiple channels? The image is actually not representing colors. We're using, and this is thanks to a very interesting PhD thesis that was done to extend the sign distance field algorithm to increase its precision, essentially. What we're doing is using the 3 different color channels of the image to represent different information. It's essentially saying, how far am I from the nearest edge, instead of the nearest part of the character. And with that information, we get nice sharp corners.
Not red, green, and blue, but other information?
We're storing
yeah.
information in the blue channel.
In the blue channel.
That helps us decide more accurately whether we're inside or outside the character. So the result of the algorithm is just a Boolean that says you're inside or you're outside. And then at that point, you can decide what color you want to make that part of the thing. But
So again, we have the rectangle where we're going to say, put the letter D for demo. And we have sampled the image file that we generated with the script, which is taking all the Latin 1 characters currently. And we're sampling it and we're saying, get us the D. And you can look at that file. It's a little peculiar because it sort of looks like it's colors all over the place. But it doesn't really look like a D. But once you take that D and you use the fragment shader, it basically says, I see what's happening here. Is that part of the D? So should I turn that pixel on? Should I turn it off? And if you're just using the sign distance field, again, the edges get blurry because it's hard to tell where you are. By using the channels, we have more information and we just have more places to ping off of so that we know if that fragment should be on or off. And because it's a fragment, it's not a pixel. So we can shade in, and as you saw, the edges of the letters were very clear. Yes?
Can you explain why the distance field is better than just the rasterization and then fill in?
can you explain why the distance field is better than rasterization and filling in?
That would have to do with, if we rasterized on the CPU, we end up with the blurriness. And we're not actually doing any calculations. By treating text as a graphics model, essentially, and then using the texture, we have a way to do it, because now if your application says, I need this font equivalent of 12 point, 16, 18, and 24, we can just change calculations, and we still have the one file that we rendered, or that we generated as a texture. You only need the texture for each different font.
But then what's the resolution of your distance field? How many pixels you have?
Excellent question. So the
Repeat
question
the
was,
question?
what's the resolution of the distance field? Well, in an odd coincidence, all of Latin 1 fits in 640 by 480. So we're back to VGA, as we started the talk with. It turns out you can use a very low resolution image to generate a very high resolution output.
Yes.
So you run like a submesh refining of kind of it on the GPU, and then define the boundary on the GPU. Like a threshold.
The question was something about a submesh refinement. Let's chat about that offline.
The basic thing is we're drawing a rectangle, we're overlaying a texture, which we got from a region of this file. So we took a font, we generated a texture, we sampled it and said, I need the letter D. And this is happening very fast. This isn't slow. I mean, we were showing it in the demo. So we found the letter D, and then we took it and put it on this rectangle. And it's like, are you on, are you off? Are you on, are you off? And the point is, it's easy when you're in the middle of the letter D, and you're in the middle portion, because you can just like look surrounding. And the fragment shader, which is very little code, it's only about 10 lines of code. But it's the edges which are hard. Yes?
How much is associated with each character in the font? How big is the texture?
The texture is 480, 640 by 480. For each character.
That turns out each character is 48 by 48, which turns out to be roughly 16 point if you use a standard 70, so just as a rough ballpark.
No, it does not distort blowing it up. I mean, we could zoom it in, I think, a little bit more in the camera, but you saw how far we took it in. The distortion does not exist, not at this one. We could actually try to use a 24 point and then scale it down, but we chose 16 because it worked mathematically really well. We couldn't find any distortion. Yes?
Well, most fonts today come with vector font type, like true types. So wouldn't it be easier to convert them in some kind of mesh and display them as triangles?
Go for it. Or repeat the question.
The question was, wouldn't it be easier to take a vector font, which is what we usually use these days, and render it as a mesh of triangles? And the answer is potentially, but not necessarily, because the amount of information that's required to do that is large, and you are generating a lot of vertices. And that's potentially slower, because GPUs are very, very good at texture mapping. It's very efficient. So there are trade-offs there, but it is far more complex to do.
Yes?
First of all, it's really cool that you guys are using SDFs to render text, so congratulations.
Thank you so much. We just got a compliment for what we're doing.
Traditionally,
Phew.
and I'm just trying to wrap my head around it, traditionally, they have issues with anti-aliasing, right? Because you're in fragment space, and you're in image space at that point. Do you see that as an issue when you're rendering your text, or is the resolution so crisp that you can just bypass anti-aliasing altogether, right?
The question was, how do you deal with anti-aliasing? Because that's an area that
Yes.
traditionally SDFs have issues with. And the answer is, from what we've been able to tell, the multi-channel SDF has such a high-quality edge that it is functionally not an issue.
When we were looking at just the distance field stuff, we could see some stuff at the edges. It was a little blurry. It was moving to the multi-channel one, because that just gives us more points to bounce off of to decide if that pixel should be on or off. Okay, yeah, let's, do you want to take one more question? Okay, one more question. Yes? Currently, we are using Latin 1. I believe the next slide is going to explain that.
Oh, it's actually a few more.
A few more slides. Okay, really quickly, as we're moving on, because we have very little time left, Vulkan. You're going to need Vulkan during development. Use the Lunar G Vulkan SDK. That's the one you want to use. It's the standard, it makes the most sense, it's the easiest. It contains the loader, the Spear V compiler, and all the tools you need for development. This is what will get you through. This is a slide of, we've narrowed it down. We looked at hundreds of websites. These are the 4 that look the best in terms of understanding all of this information and tutorials. And if you want to write the 700 lines, you can look at the first one, the Vulkan tutorial, and write those and have a lovely week, or 2, or 3. Blender, we mentioned that. If you are doing modeling and you are not using Blender, it's really cool, it's free. If you want to do modeling and you know nothing, take a look at Blender Guru. I believe he's either in Australia or New Zealand. He has a really interesting 9-part video on how to model a donut on a plate. And it shows textures, he's funny, he's entertaining. He takes a long time to explain it, but it's worth it. So there, credit to Blender Guru. The roadmap. We have more we want to do. There's more things we want in CS Paint. And part of why we're here is we're showing this early. What we showed you works, but we want more. We're hoping that somebody has information they want to contribute. We want use cases. We want to take contributors' information, and maybe you have a fragment shader you want to share. It's an open source library. We welcome you to this project. We're really looking forward to people giving us feedback. Tell us if we had too many things that weren't defaulted.
We also want to enhance our handling of distance fields so we can generate them on the fly, most likely on the GPU. We want to enhance the support for 2D graphics because that's a really important part of what we do as GUI developers, is 2D graphics.
And in terms of the text shaping, if you haven't heard of HarfBuzz, we're using HarfBuzz. It is a text shaping open source library. We use that in CopperSpice. If you've ever used any Mozilla product, like Firefox, or an Android, you've been using HarfBuzz because it's the underlying library. We happen to know the developer of HarfBuzz. He's a really wonderful guy, and he has helped us incorporate that into CopperSpice. We're going to incorporate HarfBuzz into CS Paint so that we can do Beyond Latin 1 and we can do text shaping. We may also incorporate CS String. We may have that as an option to link that together so we can go beyond Latin 1. And one of our key things that we want to do is that we want to use CS Paint in CopperSpice. And as we mentioned very early on, we talked about a surface. And what we want to do in CopperSpice is change it that when you open a window or a sub-window, behind that window is a surface. So every control you generate, whether it's a push button or a calendar or a list view or text, everything's on a surface. So we are going to migrate CopperSpice as a GUI library that everything will be done in graphics. And that will just happen behind the scenes. Not a region, the whole thing will be a surface. So we are going to use Vulkan for all of our rendering, which means high DPI gets done right. Currently in CopperSpice, there are too many places where there is a scaling factor, and that's hard to get right all the time. So we're going to take all that scaling factor out, move it all to the GPU, and then it's just going to all happen on the GPU, and the scaling just becomes so much easier. This happens to be a list of our YouTube videos, at least most of them. If you haven't seen our YouTube CopperSpice channel, we really hope you'll take a look at it. I've highlighted the 3 here. Those are the 3 we did earlier this year. Please subscribe, watch our videos, talk to us about what we've done and our work. And then we go to, yes, we talked about all that stuff. Here's how to find us. We do answer emails. We actually answer questions that are posted on our YouTube channel. You can find us. Everything's open source. We love contributors, and we love people to join the team. And I think I've been told we're out of time.
Thank you all.